Hello everyone, welcome to IIT and Gate classes. This is lecture 17 on TOC, and in this lecture we are going to start chapter 4, that is Turing machines and decidability. So we are going to start this chapter, and first we will discuss the syllabus of this chapter, and then we will move to the first topic. Okay, so the very first topic is introduction to Turing machines. Second is construction of Turing machine. Third is church Turing thesis. Then variations of Turing machines. Then RE and REC languages. Okay, then countability. Then what is problem and language corresponding to problem. Then types of problems. Okay, then we will study 6 undecidable problems of Turing machines, and the last and but not the least and very important topic, that is Rice theorem. Okay, so let me give you just brief introduction about the syllabus. So the first topic is introduction to Turing machines. Here we will study that what exactly are Turing machines, what is their capability, and so on. Second, we will study construction of Turing machines. That is, there are some standard examples which are given in most of the textbooks, like construction of Turing machine for A power and B power and construction of Turing machine for A power and B power and C power and so on. Okay, so we will study some construction, some examples for construction of Turing machines. Then church Turing thesis. Okay, so this thesis says that uh, what could naturally be called as effective procedure can be realized by Turing machine. That means for any problem, if we are able to think about procedure, then there is a Turing machine which can implement it. Okay, so there is a small difference between procedure and algorithm, and I will clear that in this topic only. Next is variations of some variation of Turing machines. So in this topic, we are going to study about some variations, like in place of single tape, we have multiple tape in Turing machines. In place of single read write head, we have multiple read write head. In place of single track, we can have multiple tracks and so on. So we will study some variations. Okay, and none of them is more powerful than the standard Turing machine. So the standard Turing machine, which I'm going to show you in this introduction of Turing machine part, that is, you can say this is the, uh, you can say this is the, what can we say? This is the mathematical model for pure for logic. This is the actual Turing machine is mathematical model for logic. So that means what? Whatever logic can do, this can do. This Turing machine can do, and this exactly is the Turing thesis. Okay, so whatever variation we do, we cannot make a machine which is more powerful than Turing machine. Okay, so we will prove all these things in this variation of Turing machine. Of course, not formally, but I will show you some basic things. Okay, yeah. Next is RE and REC languages. So actually, type 0 languages we can consider them as RE languages. Okay, so type 0 languages, or you can say language is type 0 when we have a type 0 grammar generating it. So these are RE languages, and a proper subset of RE languages is REC languages. Okay, don't worry about it. We will study them in pretty much detail. Next is countability. Okay, so which set is countable, which set is uncountable. This is very important topic, and lots of questions have been asked in various competitive exams, including GATE, NET, and so on. Okay, so make some stars on this topic. This is very important topic. Okay, and it is the base for your decidability. Okay, so next is your what is a problem, language corresponding to problem, and so on. We will study all these things. Okay, like Hamiltonian graph is a problem. Finding a Hamiltonian graph in a finding a Hamiltonian circuit in a given graph is known as Hamiltonian circuit problem. Okay, and what is the language corresponding to that problem, and so on. We will study all these things. Next is types of problems, that is decision problem, optimization problem, and so on. We will study few things in this topic. Next is 6 undecidable problems of Turing machines. Like I think you all have heard about a very famous problem of Turing machine, that is halting problem. Okay, so we will study about few problems in rather 6 undecidable problems of Turing machines. Next is Rice's theorem. So don't worry, we will study about it. Okay. If you want that I should say a few words about this theorem, then actually you won't be able to understand here, because this is you can say just introductory partner. So you won't be able to understand it. So let me dive deep into the chapter. Then we will study each and every topic in pretty much detail. Okay. So let's start the first topic, and the first topic was introduction to Turing machine. So let's start it. Okay. So what exactly is a Turing machine? So let me show you, or let me give you some informal idea about Turing machine. Then, of course, we will study the formal definition of Turing machine also. Okay. So introduction to Turing machine. See here carefully. See carefully. See, we have a tape of infinite length. Okay, we have tape of infinite length which is divided into cells. One cell store one symbol at a time. So let us suppose here we have stored A, B, A, B, and so on. Okay, so Turing machine consists of tape of infinite length. Okay, please do not write anything. I have written all the points, so you can note it down. I will give you some time to note it down. First try to listen here. Okay, first try to listen carefully, then you will get a good idea about this machine. Okay, so Turing machine consists of tape of infinite length which is divided into cells. One cell store one symbol at a time. See the first point. See, Turing machine consists of tape of infinite length divided into cells. One cell store one symbol at a time. Okay, so the next point is, see here, this is a finite portion. So this finite portion is containing the input. This is our input. So except for some finite portion which contain the input string, rest of the cell store blank. Rest of the cell store blank means what? See here, these will be blanks. Okay, rest of the cell store blank. So every book has see, different books have different notations. Some book represent blank by hash, some represent like this. Okay, some, so different books have different notation. I just want to say this thing. Okay, so but I am going to use blank like this. This is used by your famous book, Ahol Man book. So I am using that symbol only for blank. Okay, and so I think Peter Lin's book is using this hash and so on. So different books have different notation. So just it is already it will be given in your exam, in your university exam, or in gate or net and so on. In any competitive exam, it is properly given that blank is represented by which symbol. So don't worry about it. Okay, so it will be properly given to you. Okay, so I'm sorry. So what I was saying, I was saying that except for some finite portion which contain the input, rest of the cells store blank. See the next point. Except for some finite portion which contain input, rest of the cell store blank. Okay, so see here carefully, non-blank portion is finite. See here, we have only 5 cells in which we are keeping the input, or we are storing the input. So non-blank portion is finite, but blank portion is infinite. See here carefully. Okay, so there are lots and lots of cells here. Okay, or rather we should say infinite cells. So these all are blank. So except for some finite portion which contain the input, rest of the cell store blank, and this blank portion is infinite, but non-blank portion is finite. Okay, so let's see the next point. Hence, non-blank portion of tape is finite, but actual tape is infinite. Actual tape infinite means what? Blank portion is infinite. Okay. Yeah. So let's move to the next. You can say next point. See, next point is we have a read-write head. Okay, please note it down carefully. We have a read-write head, and read-write head is positioned to the first symbol of your input. So first symbol of your input is A. So here read-write head will be positioned automatically. One end of the read-write head will be connected to tape, while other end is connected to finite state control mechanism, which will store the current state of the machine. So let us suppose we are at initial state Q0. Okay, so please note it down carefully. In FA, PDA, and everywhere we have used that word read head, but here we have read write head, and one end of the read write head is connected to tape, while other end is connected to finite state control mechanism, which store the current state of the machine. I hope you know about finite state control mechanism. I have used this term many times in FA also and in PDA also. Okay, so yeah, so let's read the point. Turing machine has read-write head, which is positioned to first symbol of input string. One end of the read-write head is connected to tape, while other end is connected to finite state control mechanism. Okay, next important point is in FA also I have told you that read here in FA we have read head, here we have read-write head. So read-write head can read only one symbol at a time. Please note it down carefully. It can read only one symbol at a time, and then it will take the decision that it has to move right or left. That means what? This read-write head can move in both directions, but in FA or PDA, it can move only in one direction. So here we have a choice of moving right or left. Okay, so let me read the points for you. So next point is read-write head can read only one symbol at a time, and it can change that symbol also. This is very, very important point. It can change the symbol also. Change means what? That's why we are calling it as read-write head, na? Because it can change the symbol also. Okay, so after reading it, see, we can make it A, we can make it say C, and we can move right or left like this. Okay, see here. So I have written, so read write head can read only one symbol at a time, and it can change the symbol also, and it can move only one cell at a time, either forward or backward. Okay. Please note these points very, very carefully. So first note it down these points, then please note down these points also. So let's move to next slide. Yeah, so now we are jumping to formal definition of Turing machine. Okay, so formal definition is Turing machine is seven tuple. Okay, yeah, so FA was five tuple, PDA was seven tuple, and Turing machine is also seven tuple. See, different books are different notations. Some books says Turing machine is four tuple, some books says five tuple, but we are using standard definition, that is seven tuple, and this is also from Aho Ulman book, your standard textbook of TUC. Okay, so what are those seven tuple? Q, sigma, delta, Q naught F, tau, and blank. Okay, so let me revise you. Let me revise something. See, Q, sigma, delta, Q naught F. This was from your FA only. Okay, so FA was having these five tuple. Then tau was also in your PDA. Okay, and in PDA we were having here Z naught, na, but here we are using blank. Okay, so this is the main difference. So so these seven tuple, and let me show you something. Okay, let me show you properly what are these seven tuple. Okay, so Q, sigma, Q naught, F, all these are similar to FA, so I'm not writing them again and again. It's just wastage of time. If you are not able to follow, please watch my finite automata lecture. I think lecture was second or third. In that lecture I have told you about all this tuple. Okay, next is delta. We will jump to this delta shortly. Tau and blank. So tau is tape symbol. Okay, in PDA it was push down symbol, but here we call them as tape symbol. And see here I have written also, so I am not going to write it again and again. See here carefully. Tau is tape symbols. Okay, and blank. This is B with slashes your blank. And please keep these things in mind. Blank represent that the tape is blank. It does not represent any input. And sigma was representing what? The you can say sigma contain the input. Sigma is input alphabet. Na? That means symbols which are used to make string, which are given as input to your Turing machine. Okay, like in FA also we said that sigma is input alphabet. That means strings constructed from sigma can be given as input to FA. Similarly here also sigma is input alphabet. That means string constructed from this sigma can be given as input to Turing machine. Okay, so input, so directly indirectly I can say that input string will be made from this sigma only. Now blank must not be present in sigma, because if blank is present in sigma, then we will get confused that this blank means what? This blank means what? The input has been ended, or it is part of input. So it will create a lot of confusion. Hence, please note it down carefully. Blank does not belong to sigma, but obviously blank belongs to tau. Okay, and what does this mean? Sigma is subset of tau minus blank. See, this is blank. Okay, so let me write it properly. B, this is not B, this is blank. Okay, so sigma is subset of tau minus blank. Why we are calling like why we are saying like this? Because tape symbol means what? Whatever stored on tape is tape symbol. See, in PDA we said tau is push down symbol. So that means what? Whatever symbol we are pushing into the stack, these were known as those symbols were from tau. Similarly here also, whatever thing is stored on the tape, that is tau. So now input will be stored on the tape itself. Huh? So what can we say? That sigma will be subset of tau. Okay, so let me show you something. See, if you have a confusion, then let me clear it for you. If we have string a b double a, okay, this is string, so sigma should be your a comma b. Now the, sigma is a comma b, that's why you are saying we have constructed a string a b double a. Now this string will be given as input to Turing machine, but the question is how you will give this string as input to Turing machine. So I will say store this a b double a on the tape itself. So as soon as we store this a b double a on tape, so what does this mean? Now this a b double a become your tape symbols. Okay. A and B both will become tape symbol because we are storing them on tape. So that means what? Tau will definitely contain, please note it down carefully, tau will definitely contain AB, and it can contain some extra symbols also. So tau means what? Symbols which can be stored on tape. So let us suppose we have read write head here. Okay, let me use a different color so that you can note it down carefully. So if your read write head is here and it convert this B into C, so what can I say? This C is also stored on the tape, so hence tau will contain C also. Similarly, obviously blank is also present. Okay, so this is the basic concept about tau. So sigma is what? Whatever symbols you can say strings which are given as input to Turing machine will be constructed from these symbols, or you can say these input alphabet. So this strings which are given as input to Turing machine, that will be constructed from this sigma. Now the problem is, how will you give this string as input to Turing machine? I will say that I will store these symbols, or I will store this string on tape. Now, as soon as I store this string on the tape, it will be these A and B will become tape alphabet. Okay, so I hope I have made the point clear. So sigma will be proper subset of tau minus blank. Or sorry, proper or improper, but whatever you can say. But one thing is also confirmed, that sigma will be proper subset of tau. Okay, or you can say sigma is proper or improper. That means simply you can say subset of tau minus blank. Okay, so if you say that read write head can write only A or B, it cannot write anything extra. So C won't be present here, so it will be A, B and blank. Okay, so I hope I have made the point clear. Please do not dig deeper into this concept. This is very basic concept, and I hope you all by now you all have got the idea about it. Okay, so let's move to next slide. Please note it down carefully. Now the only thing left is delta. So let me show you something. Delta. Okay, so let me say see here carefully. So Turing machine has tape of infinite length divided into cells. One cell store one symbol at a time. So let me say we have like this. Okay, yeah. So see here, this is your read write head, and say state is q naught. Initial state is q naught. Now what should delta means what? Mapping now. So basic working of Turing machine will be like this. On q naught, Turing machine has read A. What should be done to find it? So first thing is what will be the next stage? So let's suppose the next state is q1. Okay, so as soon as on q naught Turing machine read A, or read write had read A, then it will move to state q1. That's fine. Now see, read write head should move right or left. This thing we have to specify, and the state we have to specify. Okay, so yeah, and what will be stored on the tape, that we also have to specify. So let me make it C. Okay, so move should be delta q naught A. Okay, so on q naught A is red. On q naught A is red. So now what should be the, you can say, what should be the next state? The next state should be q1, and the symbol which we have written on the tape, that is C, and we can move right or left. That means we have to give direction. So let me say we move right. So this is one of the move for Turing machine. So delta q naught A, that is q1 C R. Okay, now let me show you one more move. Let us suppose after few moves, Turing machine is at this state, or Turing machine has read this A. So let us suppose the state was q2. Okay, the state is q2. Okay, so let me write it properly. q2, state is q2. Now so let me show you the move. Delta q2 comma A. So on q2 A is read. So what should be the new state? So let me say the state is q3, and you can say symbol written is supposed, if you suppose that Turing machine has not written anything, so I will say A only. Okay, so and either left or right. So let me move left. Okay, so it's not necessary that since we have a read write head, so Turing machine should write something. No, it is not at all necessary. So I said that I have given you example. Delta q2a means q3al. I hope I have made the point clear to all of you. So let me generalize this. So generalization will be for delta. Okay, delta is your transition function. It will be Q. That means Turing machine is at any state Q, and you have read something from the tape, na? That's why you have write tau. Please do not write here sigma. Sigma is wrong because now you are because Turing machine is reading everything from the tape, and tape means what? Tape alphabet only. Okay, so please do not write here sigma. You have to write tau here. Okay, so let me write it properly. Q cross tau implies Q cross tau cross D. Okay, so this is the generalized delta for Turing machine. So what we will say, Turing machine is at any state Q, and some symbol is read from the tape. It will move to some state, it will write something, and then it can move either left or right. Direction means left or right. Okay, so please see here carefully. In case of PDA, we write tau star, but here we are writing tau. That means what? Read write head can read one symbol as well as write one symbol. It cannot write more than one symbol at a time. In one move, Turing machine can read only one symbol from the tape, and it can write only one symbol on the tape itself. It cannot write more than one symbol on the tape. It cannot read more than one symbol from the tape. I am not saying this. Delta is saying this. So it will read exactly one symbol from the tape, and it will write exactly one symbol on the tape. I hope I have made the point clear to all of you. These are very basic and very important points. Many students got confused in this delta, so I have clarified you everything. Now let's jump to the next slide. Okay, so Turing machine can act as a acceptor as well as transducer. So as a acceptor, okay, as a acceptor, it can accept type 0 languages. Okay, as a acceptor, it can accept type 0 languages. It can accept type 0 languages. And as a transducer, it extend the power of millimole machine. It extend the power of millimole machines. Millimole machines. Because in millimole machine, we have only read head. But here in Turing machine, we have read write head. Okay, let me write these points because you will get confused. In millimole machine, we have read head. We have read head. Okay. Oh, sorry. We have read write head. Sorry for that. We have read write head only. Okay, because we are writing something also. We have read write head. Okay, because we are writing something now on the tape itself. We are writing something. Okay. And in millimole machine, see the you can say, but this read write head can move only in one direction. Millimole machine, it can move only in one direction, but in Turing machine, it can move in both directions. Okay, so let me clarify you once again. In millimole machine, we have read write head, but in Turing machine also we have read write head, but this read write head can move only in one direction in case of millimole machine, but in case of Turing machine, it can move in both the directions. Okay, so that's why we are saying that it extends the power of millimole machine. Okay, so you may think that what advantage we are getting if Turing machine read write head is moving in both direction. So please have patience. I will show you. Turing machine will get tremendous power because its read write head can move in both the direction. But in millimole machine, it can move only in one direction. Okay, so I hope I have made the point clear to all of you. Yeah, so let's move to the next slide. And now I will show you some Turing machines as an acceptor. Okay, so first is Turing machine as acceptor. First question is L is equal to a power 3n, n is greater than or equal to 0. So let me make this Turing machine very easily. See, this language is regular. Please note it down carefully. A power 3n. This is regular language. If you do not know about how to recognize language type of language, then please watch my previous lectures. You will get the idea. In chapter 1 itself, I have shown you properly about how to recognize the type of language. So this is a regular language because we can construct FA for it very, very easily because number of A's are multiple of 3. So we will have 3 states only. So on the similar fashion, we will construct Turing machine. Turing machine will also have 3 states. So let me show you properly. See, this is your initial state Q0. Okay, I am directly making state transition diagram because state transition diagram is very easy to understand. Okay, so on Q0, okay, as soon as A is read from the tape, okay, now it's your choice. You keep this A as A only, or you make it as X or Y or Z, whatever way you want, you can make. So let me make it as X so that I can show you that Turing machine has read write head now, so it can change the symbol also. So let me show you. So what will you say? A is read from the tape, then it will make it as X. Okay, and it will move either right, left or right. So I will say that it will move right. It will move now the state will become Q1. Okay, or if you are not able to understand, then let me take one simple example. Okay, so let me take 6A's. Initially read write head will be here. So and state will be Q0. On Q0, A is read. Okay, and rest are blanks now. See here, rest are blanks. Yeah, so I will say on Q0, Turing machine is at state Q0, A is read from the tape. So now the question is where it will go. I will say it will move to state Q1 and I will make this A as X. Okay, and I will move one symbol to the right. That's why I have written this R here. This R means right. So now we are at state Q1. So on Q1, A is read. I will make this as X. Okay, and I will move right and I will jump to state Q2. So see here, A is read from the tape. We will make it as X and we will move right and jump to state Q2. Now on Q2, Q2 also will do the same thing. It will make it as X. Okay, and it will move right. And now please tell me what should be the state. Obviously state should be Q0. Now we are going to repeat this thing again and again. If you are not able to follow, please watch my construction of FA lectures. I think lecture 2 or 3. I have explained this clearly. So I'm making this in the similar fashion only. I'm making Turing machine in the similar fashion only. Okay. So on Q2, A is read from the tape. It will be, we will make it as X and we will move right. So again, see, we are at Q0. Now Q0, it will read this A, make it as X. We have already given the move now. X, move right. So we will jump to Q1 state. And Q1 will read is A, make it as X, move to the right, state Q2. Q2 will make this A as X, move to the right, and state will be Q0. Now see here carefully, Q0 should read the blank. If Q0 has read the blank, that means what number of A's are multiple of 3. If Q1 has read this blank, that means what number of A's mod 3, 1. That means remainder 1. So number of A's should be single A, 4 A's, and 4 A's, then 7 A's, and so on. And if Q2 has read this B, that means remainder 2. That means what 2 A's or 5 A's or 8 A's and so on. So I hope I have made this point clear, and I'm not going in pretty much detail because I have already given you the detail in the in PDA chapter. Okay, please watch my construction of PDA lecture. I have already explained you each and everything about this. Okay, so Q0 or if you are not able to follow, then just let me show you small thing. Okay, small. See here. If Q1 read A, that means what number of A's mod 3, remainder 1. Okay, see 1A. After reading 1A, we are at Q1. Nah? Again, see here, we are at Q1. So how many A's have been read? 4 A's have been read. So Q1 will say what? Remainder 1. Q2 will say what? Remainder 2. Okay, so see here carefully. Q2 read this A. That means what? Before this, we have number of A's as multiple of remainder 2. Number of A's mod 3, remainder 2. Okay, number of A's when divided by 3 gives remainder 2. See here carefully. Q2 read this A. That means what? Before that, we have 2 A's now. Okay, similarly, Q2 has read this A. That means what? Before this, we have 5 A's now, and so on. Okay, and Q0 read this blank, or you can say Q0 read this A. That means what? Before that, number of A's are multiple of 3. Please note it down carefully. Okay, so I have repeated again. Actually, I have repeated this thing in PDA also, but I have shown you again so that you get the crystal clear picture. Okay, so that's it. So this is all about your construction. Okay, and where is the final state? Actually, it's not yet over. So let me show here carefully. Okay, so what I will say here, see here. So who has read the blank? Which state has read blank? Q naught, na? So if Q naught has read blank, then it's our choice. You can make this blank as A, B, C, D, whatever symbol you want, or keep this blank as blank. Okay, so we have a choice now. So keep this blank as blank, and it's your choice. Move left or right. So let me move left, and we will jump to state Q3, and Q3 will be our final state. Okay, and please note it down carefully. As soon as Turing machine reach the final state, then it cannot read anything extra. That means what? If even if we write some move on final state, then even Turing machine won't change the state, or it won't move. Okay, or read ahead won't move. So as soon as Turing machine enters the final state, it will immediately stop and accept the string. Okay, please note it down carefully, regardless of the fact that it has read the entire string or not. So without reading entire string, also Turing machine can accept the string. The only thing is it should move to the final state. So as soon as, so let me write it properly. Okay, this is very important point, and it may confuse you. So let me write it carefully. So unlike FA and PDA, Turing machine accept the string immediately. Turing machine accept the string immediately by entering one of the final state. By entering one of final state. We can have more than one final also now. So as soon as it enters any one of the final state, it will immediately accept the string. Please note it down carefully. So unlike FA and PDA, Turing machine accept the string immediately by entering one of the final state. Okay, yeah. So and okay, and we have see, I have written immediately, but so it should be obvious, but let me write it properly also. Okay, regardless of string has been read, entire string has been read or not, regardless of the fact that Turing machine has read entire string or not. Entire string or not. These are very important point. Please make some star and note it down carefully. Otherwise, you will get confused in the construction of Turing machine. So unlike FA and PDA, Turing machine accepts string immediately by entering one of the final state, regardless of the fact that Turing machine has read entire string or not. Okay. So please, from this point, you may note that please do not make initial as final. Do not make initial as final. Why we make initial as final? To accept the null. But here to accept null, do not make initial as final. Okay, because if you make initial as final to accept the null string, no doubt it will accept the null string, but rest every string will be accepted blindly, because we have already told that as soon as Turing machine accept the final state, it will accept the string immediately, regardless of the fact that Turing machine has read entire string or not. Okay, so do not make initial as final to accept null string. To accept null string. So what I want to say here is, so directly and indirectly, I want to say, if you make this initial as final, then it will blindly accept each and every string. Okay, regardless of the string, it will blindly accept each and every string. So please do not make initial as final to accept the null string. I hope I have made the point clear to all of you. So I have made this non-final, and as soon as blank is read from the you can say tail, then it will jump to state Q3. Okay, and see here carefully. Yeah, we have written a power 3 and n is greater than equal to 0. That means what? Null string should be accepted, and here also obviously null will be accepted. See here carefully. Null means what? Nothing. Nothing means what? On the tape we have only blanks.
Null means nothing. So on the tape, we will have only blanks. So read write head will be placed on any arbitrary blank, and initial state will be there. And as soon as you not read the blank, see here carefully, as soon as you not read this blank, it will move to the final state. That's it. Okay, and it will move one symbol to the left also. So it's okay, but the state will be Q3, and Q3 is one of the final state. Hence, string will be accepted. So null string will be accepted by this Turing machine. Okay, please note it down carefully. So let me say here. Okay, so Q naught on reading blank, it will move one symbol to the left. State will be Q3, and obviously here will be blank also. But as soon as the state is Q3, that is final state, so string will be accepted. Okay. Yeah, so I hope I have made the point clear. But on the contrary, if you make Q naught as final, that means initial is final. So each and every string will be accepted. So I have told you many times, and I have repeated this concept many times. So please note it down carefully. So please do not make initial as final in case of Turing. So let's move to the next slide. Or let me put everything on one slide so that you can note it down carefully. Please note it down carefully. I am jumping to next slide. The next is L is A plus B whole star. That means each and everything should be accepted by the Turing machine. So this is very, very simple. I have already told you. So Q naught. Okay. So make Q naught initial as well as final. Okay, and make transitions for A, or see, do not, we really do not need any you can say transition, because each and every transition will be ignored by Turing machine on the final state. Please note it down carefully. Each and every transition, please, I'm dictating, note it down. Each and every transition on final state will be ignored by Turing machine. Each and every transition on final state will be ignored by Turing machine, and as soon as Turing machine enters the final state, it will accept the string blindly. It will accept the string blindly. Okay, so if you construct this Turing machine, okay, so it will accept A plus B whole star. That means all possible strings over A and B will be accepted. Okay, or if you want to make a proper Turing machine, or you can say a better Turing machine, then you should say like this: on Q naught will be our initial state. On Q naught itself, we will have transitions, because it is a non-final state. See here carefully, because it is non-final state, so we can have transitions. But it was final, so we cannot have any transition. Or if you make transitions, then Turing machine will ignore that. So it's common practice that do not give transitions on final state, because directly indirectly they are going to be ignored. So this is non-final, so we can have transitions here. So I will say A, if A is read from the tape, keep this A as A and move right. If B is read from the tape, keep this as B only and move to the right. So A and B, each and every A and B will be read, and after that, as soon as blank is read from the tape, keep it as blank only. Left or right, it's your own choice. Move with the left or right, and we will jump to state Q1, which will be our final state. So the basic difference between these two Turing machine is that it will read the entire string and then it will accept it. But here, without reading, it will accept the string blindly. It will say yes, yes, yes. Whatever string you whatever string you give to this Turing machine, it will blindly accept. It will blindly accept it. Okay, and please note it down carefully. Here our assumption is that sigma is A comma B. Okay, so directly and indirectly it will accept all possible strings over A and B. And if we assume sigma is A B C, then the same Turing machine will accept all possible strings over A, B, and C. That means, see, if this is the scenario, let me use a different color. See, if this is your scenario, then this Turing machine will accept this L. But if this is the scenario, then the same Turing machine will accept L as A plus B plus C whole star. Okay, so if we have a question on Turing machine that what language is accepted by this Turing machine, then we will say no comments. Please tell me something about sigma. If they say sigma as a comma b, you will say this Turing machine will accept a plus b whole star. If sigma given is a b c, you will say the same Turing machine will accept a plus b plus c whole star, and so on. I hope I have made the point clear to all of you. Okay, but this Turing machine is, you can say, is much better because here we do not need to specify the sigma. Okay, so we will directly say that every possible string over a and b will be accepted by this Turing machine. Okay, I hope I have made the point clear to all of you. Let's move to the next slide. This is very important question. Please make some star on it so that you can get the crystal clarity. See, sometimes the question is about construction. That means given a language, try to construct the Turing machine. And sometimes reverse questions are also asked. That is, given this Turing machine, find the language accepted by this Turing machine. Okay, so let me show you something. So if, see, null is accepted or not, tell me something about it. Null is accepted or not? Null string is rejected. Why? Because on initial state, we have to read A or we have to read B from the tape. Then we will jump to Q1 and Q1 will read the blank. Then it will move to state Q2. So Q0 cannot read blank. Please note it down carefully. We have not given permission to Q0 to read the blank. Since Q0 cannot read blank, that means what? Null string won't be accepted, it will be rejected. Because if we have a move for the blank, okay, on Q0, then we can, and that after reading that blank, we are jumping to final state also. Then we will say that null is accepted. Let me show you something. If we have a move like this, blank, blank, R, right or left, whatever direction you want, blank, blank, R, and we are jumping to Q2. Now we will say that null will be accepted. Otherwise, obviously, null will be rejected. So here we do not have provision to read the blank from Q0 and move to final state. So now I can say that null is rejected. Okay. Now let me show you something. So since it is your first example for recognizing language, so let me show you step by step. Null is rejected. What about my single A? See here carefully. See the transition on Q0. As soon as A is read from the tape, we will keep this A as A and Turing machine will move to the right and move to the state Q1. So according to it, I can say on Q0, A is read, then it will move one symbol to the right and the state will be Q1. Now here, since I have said that we have single A as a string, so obviously next symbol will be blank. Now what will you say? Q1 on reading blank, it will move to state Q2. So hence single A will be accepted. Similarly, you can check it out yourself. Single B will be also accepted. Now let me show you one thing. Okay, see now carefully, otherwise it will trouble you a lot. Null is rejected, A is accepted, B is accepted. Now jump to two length strings. That means double A. Now see carefully, otherwise it will trouble you. Please see here carefully. See on Q0, A is read. Q0 A is read. It will keep this A as A and move to the right on state Q1. Okay, so it will move to the right, it's state Q1. Now see here carefully. If Q1 will read blank, then it will go to Q2. But if Q1 read A or B, if Q2 read A, then it will keep this A as A and move to the left. Or if Q1 read B, then it will keep this B as B and move to the left. So now Q1 has read A. See here carefully. Q1 has read A. So it will jump to the state Q0 and move left. So now read write head will be placed again here. Okay, and state will be Q0. So now this Q0, okay, or let me show you like this. Yeah, so let me use another color. What I will say, we will add Turing machine will be at Q0. Now on Q0, if A is read, See here carefully. Q0 A is read. So that means what? It will move to Q1 and read once and move right. So it will move here with the state Q1. Now Q1 is reading A. Now I think you have got the idea. Q1 is reading A. So it will move one position to the left and state will be Q0. State will be Q0. Q0 will read A. It will keep this A as A and move one symbol to the right and state will be Q1. Now I hope you have got the idea. Turing machine will not halt and it will keep on rotating between these two states Q0, Q1. That means it will go to infinite loop and this is known as hanging of Turing machine. Hanging of Turing machine. So Turing machine hang means what? It will obviously reject the string. Why the string will be rejected? Because whenever double A is read from whenever string is double A, Turing machine is hanging. That means directly and indirectly it is not moving to the final state. And since it is not moving to the final state, so obviously string will be rejected. So hang means what? String is rejected. Okay, so Turing machine has one possibility of hanging also, and this Turing machine hangs on double A. Now this is homework for you. This is homework for you. Please verify yourself. On double B also it will hang, on AB also it will hang, on BA also it will hang, and so on. So for all the strings it will hang. So it won't hang for null, because Turing machine will halt in dead configuration, because on Q0 we have no choice of reading blank. So on null Turing machine will halt, but it will reject because it will halt in a dead configuration, because we have not specified the state on which Turing machine will go whenever blank is read from the tape on the state Q0. Okay, or Q0, whenever Q0 read blank from the tape, then we have not specified the move. So I will say that Turing machine will halt in, or you can say Turing machine will halt, but it will halt in dead configuration. Hence string will be rejected. So null will be rejected, but Turing machine will halt and reject it. Single A will be accepted, single B will be accepted, but rest of the strings, it won't accept, because Turing machine will hang. So Turing machine will hang on each and every string of length 2 or more symbols. And in fact, by now you have already guessed, if we have triple A, then this A won't be read by the Turing machine, because it will keep on rotating between these two A's only. Please try to visualize this thing. I am not going to speak it again and again. Try to visualize it yourself, that on double A, Turing machine will keep on rotating between these two A's only. It won't be able to read this A. So hence directly and indirectly, what can I say? For each and every string of length 2 or more, this Turing machine will hang, and hence all the strings will be rejected. Null will be rejected, but single A and single B will be accepted. So please, if the string is accepted, that means directly indirectly we are saying that Turing machine is halting. Okay, so for acceptance, Turing machine must halt in a final state. So let me write everything properly so that you can note it down and it won't confuse you. Please note it down carefully. Now I am writing few points for you. So the very first and the very basic or important point is what? Very basic point is what? Let me use a different color so that you get proper clarity. So the point number 1 is what? Turing machine will accept string by halting, accept string by halting in one of the final state. In one of the final states. Point number 2. Turing machine accepts string by halting in one of the final state. Okay, so Turing machine can reject string Turing machine can reject strings by halting in non-final state. Okay, by halting in, or let me say here carefully, by halting in dead configuration. By halting in dead configuration, because for non-final state we have only two choices, na, either left or right. Okay, so Q0 is non-final, Q1 is non-final, so we have only two choices, that is left or right. So read write head should move in either left or right. Okay, so I cannot say that Turing machine halt in non-final states. Yeah, obviously I can say this when I will show you variation of Turing machine. In variation of Turing machine, I will say that each and every non-final state will have three choices, either left or right or halt. Okay, or halt means what? It is moving nowhere. So this capability, or you can say this enhancement, is in variation of Turing machine. In standard Turing machine, non-final state will have only two choices. That is, for non-final state, that is either move left or right. It cannot halt in any non-final state. For halting, it have to jump to final state, or it have to halt in dead configuration. Or you can say that move is missing. If move is missing for any state, then I will say that Turing machine is halted in dead configuration. But if you can, or another way of halting is halting in a final stage. Okay, but in a variation of Turing machine, in a small variation of Turing machine, we can have a possibility for a non-final state to move either left or right or move nowhere. Okay, this is variation case, and this is your actual or standard Turing machine case. I hope I have made the point clear. And now, if you are not able to follow, don't worry. I will show all each and everything in pretty much detail in the topic of variations of Turing machines. Okay, I'm not going. My intention is not to confuse you. I'm just giving you some idea. Okay, so Turing machine can reject string by halting in dead configuration. Okay, yeah, that's it. So we have only one choice for Turing machine to reject string by halting in that configuration, or and another choice for rejecting is hanging. Okay, so third point is Turing machine can reject string by hanging also. Turing machine can reject string by hanging also, by hanging. And I have shown you clearly that Turing machine may not halt. That means it can hang, and this hanging is because Turing machine has choice of either moving left or right. So by this choice, we have shown that it can hang also, left, right, left, right, left, right, left, right, left, right. But PDA, FA, they will always halt, because the read right or read head can move only in one direction. Okay, so because Turing machine read head can move in both direction, so it has a choice that okay, so let me let me say it again. See, Turing machine has a choice. That means its read write head can move either in left or right, and because of this choice, Turing machine may not halt. Okay, so halting problem of Turing machine is coming just because its read write head can move in both the directions. Okay, and formally I will define halting problem in pretty much detail in the subsequent topics. Okay, and I will show you, in fact I will show exactly about halting problem in the sixth undecidable problem of Turing machine. Okay, let me show you the topic again so that you get the idea. Yeah, so here I will show you halting problem. Please do not get confused. I have used the word halting problem so that I can show you that Turing machine may not halt. The actual halting problem is completely different. I will show you in this topic, that is undecidable problem of Turing machine. I am just saying that Turing machine may not halt. Okay, so that's why. Okay, so Turing machine can reject string by hanging also. Okay, so the halting problem is actually different thing, and please do not get confused. And I do not know that why I am using this word. I just want to clarify you, or I just want to give idea about Turing machine may hang. So I am using the the terminology for the Turing machine may hang as halting problem, but actually halting problem is different scenario or different problem. I will show you detail about this problem in subsequent topics. That is 6 undecidable problem of Turing machine. I will show you a complete idea about what exactly is halting problem. Roughly, I am saying that Turing machine may hang, and I am saying that as halting problem, but actually it is not a halting problem. Okay. So I have repeated many times, and I hope I have made the point clear to all of you that Turing machine may reject string by hanging also. That means Turing machine has halting problem. That means it may not hang. Sorry, it may not halt always. It may hang. So it may hang, and I'm saying it as halting problem. Okay. Yeah. So see, we have just to give you summary. We have 3 points. So Turing machine will accept string by halting in one of the final state. Turing machine can reject string by halting in that configuration. Turing machine can reject string by hanging also. So for acceptance, let me use a different color. For acceptance, Turing machine has only one choice. What? Halt in final state. Halt in final state. For rejection, Turing machine has 2 choices. First, halt in dead configuration. Second, hang. Okay. So please note this point very carefully, otherwise it will trouble you a lot. Okay. So now the main thing is for actual Turing machine, each and every non-final state, we have only 2 choice for read-write head, that is move either left or right. It cannot stop. Okay. So for non-final state, we have only 2 choice, that is left and right. But in one of the variation of Turing machine, we have a choice of not going anywhere. In non-final state also, Turing machine can halt. Okay. In non-final state also, Turing machine can halt. This is a variation, but in standard or actual Turing machine should move either left or right in case of non-final state. But in case of final state, we are not giving any move. So directly, indirectly, we are saying that Turing machine is halting. I hope I have made the point clear. Please note these points very carefully, and I'm jumping to next slide. Okay. Yeah. So next question is a power n, b power n is greater than equal to 1. So you have to construct Turing machine for this language, and this is homework for you. And of course, in the next lecture itself, I will show you about the Turing machine. Okay, and just let me just give you a small hint here. So what will be the logic? Let me just clarify you the logic. See, if we have 3 A's and 3 B's, and here we have blank. Okay, so on Q0, whenever A is read, or let me give you brief introduction because proper logic explanation will take some time, and already 1 hour is over. So let me give you small hint. That means we will make this first A as X, move to the right. As soon as B is read, we will make this as Y. Then we will move again back and move make this A as X, make this B as Y, make this A as X, make this B as Y, and whenever we will see that these number of X and number of Y's are equal, or you can say we have made X as well as Y's. Now, so we have cut this A, make it as X, we have cut this B, make it as Y, and so on. So in the end, we will say that nothing is left, neither A nor B, nothing is left. So string will be accepted. Roughly, of course, I do not think that you have got the clear idea, but I have just given you small hint about how the string will be accepted by the Turing machine A power n, B power n is greater than equal to 1. Okay. So don't worry if you are not able to follow. Don't worry. In the next lecture itself, I will give you crystal clear explanation about how to construct Turing machine for this A power n, B power n, and it's your homework. Try to construct it yourself, and of course, in the next lecture, I will show you. Okay, so the basic idea is cut this A, make it as X. Now cut this B, make it as Y. Come back, cut this A as X and cut this B as Y. Come back, cut this A as X, cut this B as Y. in the end you see that neither A nor B, nothing is left on the tape. That is, we have only X and Y's. That means what string will be accepted. This is the rough idea, and I will clear it properly in the next lecture. Okay. Yeah. So thank you so much. Bye-bye. We will meet in the next lecture, and I will start the next lecture from this question itself. Okay. Thank you so much. Bye-bye.